Welcome to Frank Stajano Explains, and Merry Christmas, by the way. Today's topic is writing binary files. I will be teaching a new security course in 2022, so this video is an extra tutorial in preparation for that. To do well in security, you need plenty of practical skills in many diverse areas of computer science, and I imagine most of you already know how to write binary files, which is not a big deal. So if you already know, that's great. In that case, you don't need this tutorial. Here's a quick self-test you can do in 5 to 10 minutes to figure out if you should be investing your time in watching this video or not. The problem is not supposed to be intellectually difficult. It's pretty basic stuff actually, but I know there still exist some computer science students who can't do it. And those people had better learn how to do it before they start my security course, otherwise they won't be able to follow. So here's your task. Make a file exactly 537 bytes long, containing the following stuff. Starting at offset 299, where 0 is the first byte in the file, so you go forward until 299, there should be the null-terminated ASCII string frankstajanoexplains.com. Starting at offset 192, there should be a little-endian 64-bit representation of the integer 3,735,928,559. At every offset that is a multiple of 128, there should be a big-endian 4-byte representation of the same integer as I mentioned before. At any other offset in the file, any offset, say I, between 0 and 536, there should be the byte value I plus 100 modulo 256 if it was a position not covered by any of the conditions I already mentioned previously. So that's the end of the question. Imagine this were an officially marked portion of your coursework, so you got grades for doing it well. It isn't, but just pretend. If you have no trouble creating a file with the above content byte for byte identical to the reference one I have on my website at the address below, then you're doing fine and you may safely skip the rest of this video unless you really have nothing better to do. If instead you would find yourself in trouble with this problem and you would like some assistance, then click the like button, subscribe and stay tuned, and this video is right for you and will teach you all you need. The self-test I just gave you is representative of the kind of stuff you need to be able to do to craft a security attack. You must build a binary file with certain specific content, poke some values into it, perhaps memory addresses at a specific offset in your payload, and so on and so forth. Convert between hex and decimal, reverse things, big-endian, little-endian, and so on. It's not difficult. None of that is difficult, but you must become fluent at doing that if you aren't already. I'm going to go through a series of simple exercises that build up towards this self-test problem. This is a tutorial, and for this reason it is much slower than my regular lectures. I'm going to share my screen and do the exercise in real time, talking you through what I do, mistakes included. First, I'm going to do them in C, because C is a low-level language that lets you do anything you need to do with the machine, and if you're going to be serious about security, you just cannot ignore C. Then I'm going to redo the same exercises again in Python, which is a very practical, powerful and enjoyable tool you also want to be fluent in. I've left all the questions in the description below, so you can try doing the exercise on your own without watching the video, and you can then use the chapter markers to skip over the bits where you don't need an explanation, so that you go directly to the parts where you did get stuck when you attempted them on your own. Feel free to use this optional supporting material in the way that is most useful to you. And with that said, let me share my screen. Alright, so here's a transcription of the self-test I just gave you. Stop the video, try doing it. If it's too difficult, then watch the rest of the video. As for us, let's start with the basics. How can you read and write arbitrary binary files? Well, binary files have values that are not just text. With text file it's very easy, and I'm sure you've done at least that many times. So I made myself a few exercises here, and this first one, exercise 0, is not even worth mentioning. Write the characters of the string hello world to a file. Okay, so what you do is you write echo hello world. This goes to standard output, and you pipe the standard output into a file. Exercise 0 dot text isn't text of the exercise, it's called bin for a binary file, which is a binary made only of text characters. Am I right? Well, hello is a 5-letter word, world is another 5-letter word, and in between there's a space, so that should in total be 11 characters. But here I see that this is 12 characters, this file over here, length is 12, and the reason you imagine is because there's a new line after this hello world, so that if I write x0 bin x0 bin, if I concatenate 2 copies of this file, then I get the output in 2 separate lines, because there is a new line at the end. The 12th character here is a new line. If there were only 11 characters, then I would get hello world, and then another hello world with a capital H attached to the lowercase d over here. So what if I wanted to have only the letters and not the new line? Then I would at this stage say echo -n, which would then produce a file of 11 characters, and if I then were to concatenate 2 copies of it, then I would get what I just said, hello world, then hello world without a new line, and even the prompt for my command line without a new line. All right. If I wanted to look at this file other than by cat, because with cat I can just see the printable things by concatenating, well, the file to itself, sending it to standard output, I could use a tool called hexel mode. So if I open the file in Emacs here, x0 bin, then this is what I see, and I can see if I try to go to the end that it doesn't go any further than this, so there is no extra new line. I can say hexel mode, and it will show me the file in this format, where I see the bytes that make up the file, like that, and then the textual version here on the right. So if you're not familiar with the ASCII table, let's just put one up. I prepared one earlier here, and so this thing, stick it here at the bottom for reference. Let's make this one a little shorter so it doesn't overlap. This here shows this 48 hexadecimal, so that every byte fits into 2 digits. 48 in hex is over here, is the character for capital H, which is what you expect, and you can see the transcription here. H is 48, and the next one is this 65, which is the lowercase e. 65 hexadecimal is 65. Over here is the lowercase e, and so on. So this is a view of the file like this. And if you don't remove any line at the end, if you output echo hello world like that, and then you refresh this file, then you see now it does have the final new line. And if I go in hexel mode again, then I see that it finishes with this. This is represented as a dot because all the non-printable, non-text characters are printed as a dot, and it's aliasing the actual dot. And so this 0a is what it actually is, and 0a, if I look it up in here, is line feed, new line, line feed, new line. This is this character here. Now this is a line feed in the Unix world, is the way to terminate lines, and in other operating systems, well, nowadays almost everything does that. If I go here and I say, okay, use the DOS line terminations, actually I'm changing the wrong file. If I go here and I say change this to DOS line terminations, and I save this file, then what happens to it over here? it's now become 13 bytes instead of 12. And if I look at it in my hexel mode, then I see that I now have two special characters after hello world, and they are 0D and 0A. 0D is carriage return and 0A is line feed. So in DOS you terminate each line with carriage return line feed. Sounds very how to say low level, and just the way that the carriage would first return to the left of the line, and then the line would be fed in a typewriter. You would have to specify those directions separately. It seems to be wasteful to waste 2 bytes to say that that's the end of the line, and that's why Unix only shows the line feed for new line. And the world doesn't end there, because there's yet another convention which was used by the Macintosh before OS X, which was to terminate the file only with a I have to refresh this. Hello world, hexel mode. And here lines are terminated only using a carriage return, and here I've got 2 carriage returns. So there's a line with hello world, and then an empty line after hello world in this file. This transformation has changed the line feed into a carriage return. So we have two lines in this file over here, but it's using this Macintosh convention, this old Macintosh convention. And if I were to go like this, I can see that there's an empty line, and that's the 2-line file. So if I replicated this line several times like this, and just for simplicity I got rid of this empty line at the end. So this is 5 copies of the hello world line, and I save that with a Macintosh convention. And if I look at it again in hexel mode, yeah, then you see that there's these copies, each of which is terminated by this 0D carriage return. What happens if I display this file? Now, this is using the old Macintosh convention. This is instead the normal a Unix environment. So what do you expect to happen? It will do a carriage return without doing a line feed. So it will basically overwrite itself. Cat x0 bin. Wow. So what did happen? What happened was that executing this command printed hello world, then did a carriage return, which returns the carriage, like the writing head to this position. Then he wrote hello world, then carriage return, then wrote hello world, like this 5 times. And then after that, the shell bash wrote its own prompt from the place where the cursor had been left. And that's that LD that you see here is the leftover from what had been printed there. So if I had written something shorter than the prompt, it would have been completely hidden by the prompt. Or if I had had a longer prompt, if I say, okay, export ps1 equals a longer prompt, like that. So now I have a longer prompt, and if I cat this x0 bin, it's completely obliterated by my prompt. Interesting. And if I look at it, instead it's 60 bytes. Okay, it's the stuff that we see over here. So if we convert it back to the Unix line ending convention, it will still be 60 bytes, but the carriage returns will be turned into line feeds. So now I go here, I save it, and if I list it, directory listing is still 60 bytes, but if I cat it, something went wrong. Didn't convert these carriage returns into new lines. Something went wrong because I did the conversion while I was still inside the hexel mode. So what I should do, so So no further undoing from it told me that it wouldn't undo. I can just substitute those things. Substitute Control M with a line feed. Alright, so this file now has proper line feeds as we expect, and still 60 bytes long, and if I display it, then it displays what you expect. Okay, so I'm digressing. I should try not to digress, otherwise we'll be here forever. Another way of viewing this file would be with a tool called OD. OD stands for octal dump. If you octal dump x0 bin, you get this load of rubbish, where these things are octal characters. Now, octal characters is the stuff of dinosaurs. You know, when my father was working for IBM and there were mainframes with 36-bit words, then octal made some sense. But nowadays everything is nice powers of 2. So you have, you know, I went from 8 bits to 16 bits to 32 bits to 64 bits. Then nobody wants octal, you want hexadecimal, and so to do that you have to say the type is going to be X for hexadecimal, and then you see hex numbers, and if you want to say X1, I think is the syntax, either 1 byte at a time and separate them, otherwise it was chunking them up into 4-byte words, and also reversing them, and we'll get back into that. So this is the same stuff as we would see basically here. Hexel mode helps find the type property. Mode. Okay. Yes, go for it. And so here we see 4865, 6060, 4865, 660. Except here we have also the nice printable thing, and we can get that with octal dump as well. If we say z, it means show me the printable stuff over there. Hello world, with nice boundaries so that we don't get confused in case there are space. Okay, so that octal dump is a command line version of basically what you get here in this hexel mode. And you have other things for changing the address from between decimal binary and all sorts of other things. Anyway, there's a man page if we need to. So let's replace this with exercise 1. Exercise 1 is write 1984, title of a famous George Orwell science fiction novel. Science fiction then, because it was written while 1984 was in the future, to a binary file as a C short int, then a regular int, and a long int. So the lengths of these things depend on the machine you're on, and nowadays, well, in theory this could change depending on the architecture of your computer. Nowadays on my 64-bit machine, then short int I expect to be 2 bytes, a regular int 4 bytes, and long int a full 8 bytes, 64 bits. So write 1984 to a binary file as a C short. So that we're getting into the meat of actually writing a binary file instead of just a text file. So we had been writing text stuff with the new line, which was a kind of non-printable binary kind of stuff as a side effect. But if I actually want to write binary, a short int, okay, so 1984. First of all, we have to figure out what 1984 is in binary. So what's 1984? 1984 is equal to, certainly there's a 1024 in there, plus, let's whip out a calculator. So, (1984) minus 100,024 gives me 960. So there's a 512 in there, I'm sure. Minus 512. 512 gives me 448, which surely has a 256 in it. And then no 192 surely has a 128 in it. Not plus. Over here we want a minus. That's a 64, okay, plus 128 plus 64, and we are done with the powers of 2. So this is, in binary, 1984 would then be 1 for this, 1 for that, 1 for that. They're all consecutive. 64, then there's a 32, then there's a 16, there's an 8, there's a 4, there's a 2, and a 1. So that's what this looks like in binary. So I got 4 zeros here, 1 1 0 0 here, and 1 1. If I write them in groups of 4, 0 1 1 1, 1 1 0 0, and 0 0 0 0. So in hex, this 0 1 1 1, this is a 7, this is a C, and this is a 0, right? So please be fluent with this kind of stuff, and we can check by typing this 1984 in here, decimal, yeah, and we want it in hexadecimal, 7C0, great, okay. So 7C0 is how I write this in hex, this is how I write it in binary. Right, 1984 to binary file as a C short int. What would the C short int be? So we said that I expect the C short int in my machine to be 2 bytes. Well, we can check that by saying, okay, this is the exercise text. Let's make a C program. Write this as x1c, and I'll make this into a comment that says what should be in this C file. Okay, and the first thing I'm going to do is int main. First of all, check the sizes of my int. So I'm short. I expect this to be 16, and I expect this to be 32, and I expect a long int to be 64. So let me see that I got this right. The 16 is indeed 2 bytes and so on. Print first size of short int equals size of x16. Size of int equals size of x32 and size of long int there. Okay, and we need to include okay, GCC exercise 1C. That's not good. %d. Okay, so we execute this program, and it says, okay, it says you should have added those damn new lines. Recompile this piece of rubbish, and okay, size of short int is 2 bytes, size of int is 4 bytes, size of long int is 8 bytes. Okay, so that's all as expected. So these numbers 16, 30, and 64 are right, and that's all very good. So let's now do the exercise, which was write 1984 to a binary file. And so I'm going to say this is equal to 1984. And this one 2, and this one also 1984, and then I'm going to print this as a short int, regular int. So in memory, I have this as a short int, as an int, as a long int, and now my problem is how to write this to a file, not as text, but as bytes. So how do I write to a file? How do I write to a file? There is a function in the C library called fwrite, for file write. And so write. How does it work? Fwrite, okay, const void pointer. The function fwrite writes n memb items of data, each size bytes long, to the stream pointed to by stream, obtaining them from the location given by pointer. So first we need to make this stream. I'm going to make this stream. File pointer equals open. Let's call it exercise 1 bin for writing in binary. And what we do is not print, but fwrite to from the location given by pointer, which is going to be x16. I'm going to write next thing is the size, and the size is this, and then the next thing is how many, just one, thank you, and then where I write it to fp, my file that I've just opened, x1 bin. All right, so now a couple more of those, and get rid of those, one more, and I'm gonna do 32, and 64, and the 64 over here. So I expect this to write first the 2 bytes of 1984 in here, then the 4 bytes of this 1984 with the top 2 bytes equal to 0, and then 8 bytes of this other 1984 with the top 6 bytes all equal to 0, all into a binary file of length equal to 2 plus 6 plus 8 equals 16. No, 2 plus 6 plus 8 equals 14. Let's compile this. Right, what about that? Open, is it? Okay. Right out writes something to my file, so I should now have my 14-byte file. There we go. And if I look into it with that od command that I showed you earlier, x1 bin, then what do I get? C007, C007, what's all this rubbish? Well, I was going to have 7C0. Of course, in bytes, it's going to be 07C0. But here I have C007. Why? Because in this processor architecture x86, as in several others, the numbers are stored in little-endian fashion. Little-endian means that first you have the least significant part of the number, and then as you go to the right, or as you go to higher memory addresses, then you get the most significant bit. So this is one of 2 possible conventions, little-endian and big-endian, and both of them make some sense if you follow the argument, and make no sense if you hear from the other side. So big-endian is how you write things normally. So this is big-endian because the biggest end of this 1984 is the 1, which is worth 1,000. This one is worth 9 times 100. This is worth the column of the tens and the columns of the ones. And so the column of the thousands is the heaviest and is the big end. And so this is how you write and how you do arithmetic normally. So why would anyone in their right mind write this as 4, 8, 9, 1 in reverse. That would be the little-endian version. So this is the units, this is the tens, this is the hundreds, and this is the thousands. And in any base, of course, this is in decimal, and you could have little-endian in binary or in hexadecimal or whatever you do. Or this is even in base 256, because this is the least significant byte and then followed by the next significant byte and so on. What's the point of little-endian? The point is that if you were to add up, for example, two numbers such as this one and let's add 128 that we have here, and you do them like this. Let me write here. If I try doing 1984 plus 128, then I get into trouble, because this one is 1,000. It should not be added with this one, which is 100. So this will only work if I align them by doing this. Now, if I use little-endian, then, and if I write the other thing I wanted to add, which was the 128, if I write the 128 in little-endian, then they are immediately aligned. So I'm adding the units with the units, and I can do that, and then I have a carry, and I add the tens with the tens, and then I have a carry, and I add the hundreds with the hundreds, and if I have a carry, then I carry it over to the thousands and so on. This is great because I can start where the numbers start without having to first check how long they are. In this case, I have to check, oh, this one is short, so I have to shift it, and then I can start doing the addition, and I move on forward with the carry, whereas here I have to basically align them like this, and then start from the other end, start from the units which are now on the right, and I go backwards like that. So in some sense, you can see that, certainly from the point of the machine that finds these numbers in memory, which can be of different lengths, little-endian can be seen as making life more convenient. So basically, the x86 processor family and several others that are in common use today all use little-endian, and this is why you find these numbers stored as little-endian. So the short hint here is least significant byte and the next one, and then the 4-byte int is least significant byte, the next one, and then there's nothing, so 0 filled for the top two most significant bytes, and the 64-bit version has again only the bottom 2 bytes, and then the rest is filled up with zeros for the most significant things. So this is our exercise 1 done. All right, good. So what have I got in store for you next? Let's get ourselves another exercise. Exercise 2. C, no, got it wrong. Exercise 2.text I meant. Okay, right, minus 1 1984 and plus 1984 to binary file as a short, int, and long. Okay, let's just copy this text and refresh. Reinsert the previous program to save a bit of typing, so I retype this in here to do the exercise 2, and I can recycle most of this program. I have to write it into exercise 2.bin minus 1984 and 1984. Okay. All right, let's call the minus ones y. Okay, it doesn't look like there's much to this exercise other than changing these x to y's. Okay, enough. Let's give it a go. So let's compile exercise 2 and run it. And let's have a look at this output. And what do we get in there? This is disappointing, and that's because I didn't put the minus sign in front of these things. So minus sign, and minus sign. Actually, it would be more proper to say what I expect to find in this file before actually generating it, so I can check if I made any more boo-boos. Right, so minus 1984 is the negative of this, and the negative of a binary number would be obtained by flipping all the bits and then adding 1. So if I flip all the bits of this thing, then that's 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1. If I add 1 to this, then and I have to start from this end, then this 1 plus 1 makes 0, carry 1, 1 plus 1 makes 0, carry 1. And basically, it's very inconvenient to write like this because it adds 0. Anyway, all these things become 0, 0, 0, 0 until I carry a 1 in here, and then they all stay what they were. So if I write it from this end, then 1, 0, 0, 0, 0. This one is the one that gets the carried over 1, and then all the rest is 0, like that. So that's what I expect. So this was this. And now this one is going to be, this is 8, this is 4, and this is 0. So I expect, so 7C0 is 1984, and this is minus 1984 in a 2's complement. So 0840 is what I expect. I expect to see in little-endian 4008, then 4008 0000, and then the same with 4 more zeros at the end. 00, like that. Followed by what I had before. File to save in. No, I didn't mean to say, just to have it. Okay, so let's compile this. Save it first. Save, compile, and run this and see what came out. 40F8, 40F8, FF. Ah, idiot. Yes, of course. So the 2's complement filling of a negative number would have to be F's, 1's, not 0's. That's bad mark. Bad. Okay, and this is all F's over here. Okay, FF, blah, 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 blah. And that's indeed what we see. Okay, filled with F's, filled with F's, filled with F's. And then after that, the stuff that we had earlier, which is C007, which is this one in reverse C0 and 07. Then, because it's positive, 0 filled. All right. That's exercise 2. Let's have a look at exercise 3. Exercise 3. Write to a binary file the numbers from -10 to 10, first assigned shorts and then assigned longs. How long would the file be? Well, the signed shorts will be 2 bytes each, and there's from -10 to 10 there's 21 because of the 0 in the middle, and the signed longs are 64 bits, so 8 byte longs, 8 bytes long, and so 8, that's again 21 other, so 8 and 2 makes 10, so there's 21 times 10 total occupation, so 210 bytes should be the length of this file. So let's see what we can recycle from exercise 2.c. And write this out to exercise 3.c. Okay. What do we do? Write to a binary file the numbers from -10 to 10. Okay, so this goes to exercise 3.bin, and we make ourselves nice for I int I equals -10, I less than or equal to 10, this wants to be a close bracket. We f right. So you have to remember the order of these parameters in here. That's the place where we get the stuff from, and so the place we get the stuff from is address of I. So this is short int I, then size of I, and I want 1, and I write it to the file, that's okay, and then as assigned longs, so I recycle this, but this time my counter is a long. Okay, don't need any more of that stuff. And let's compile this exercise 3. Run it and see what we got. First we expect exercise 3 to be 210 bytes, we said. Yeah, that's good, 210. And then let's run this OD to see what's in it, and what we expect in it is first the numbers from -10 to 10. What's -10? Okay, that's just for the sake of not spending the whole day. -10, I want to do decimal here, -10 in hexadecimal, -a. No, I want to see it in banner. How do I do that? Well, clearly this doesn't have. Okay, so in that case, let's do it manually. Probably takes less time than trying to figure out this calculus. So 10 in banner is this. If I'm going to do -10, I need more space, so let's add. Make it a byte, okay. So to do the 2's complement, I first do the 1's complement, and then I add 1 plus 1. Then 1 plus 1 makes 0 with a carry of 1, which stops here. So the result is going to be this 1, 1, 1, 1, and then 0, 1. This is 1, 0. Okay, so this is 4 plus 2 is 6. So this one is obviously f, and this is 6. So I expect the first thing, which is -10, to be f6, but in 2's complements it would be extended, would be in f6, which in little-endian would appear as f6, ff. And then the next one, -10, -9, -8, and so on, it would be just keep counting up by 1, so f6, f7, f8, blah, blah, until we get to 0, and then keep counting up. And then I would have the same thing, just sign extended to 64 bits. Let's see if that's what we got. Okay. f6 ff, f7 ff, f8 ff, f9 ff, fa ff, all the way up to ff ff, which is then followed by 0 0, 0 0, then 0 1, 0 0, just as expected over here, until we run out of the short ints with 10, which is 0a, 0 0, this one, and then we start again with -10 f6 ff ff sign extended to 8 bytes, and then f7 ff sign extended to 8 bytes, then f8, blah blah, all the way to 0, and well, ff, then this is -1, and then 0, and then 1 and 2, and so on, all the way to that. And this is all great, excellent. So we sorted our exercise 3. What else have we got in store? Exercise 4. Exercise 4. Write a 128 byte binary file containing at offset 96 the dotted quad blah blah as 4 byte big-endian. Everywhere else the byte for it. That starts to look slightly more similar to what I gave you as a kind of self-test. Let's see what it takes to do that. Include the previous one, exercise 3C. Save this into exercise 4C, so we get it colorized as well. Write a 128 byte binary file. Of course, we still need a file to save too, so we'll keep that and make it 4. We are going to make a buffer of 128, so it's going to be character takes a byte, B 128, and the last line of my file is going to be this fwrite. So this was where I get the stuff from B. B is already okay. That size of B 1, or I could have said 1 and 128 times, and I send this that, and that will print out my whole buffer after I fill it in. So now I first need to fill it in for short. We don't need short, but never mind. I from 0 to 128. What do? I stick in there byte 42. So B I equals I don't even need 42, and that fills up the background of the buffer. And at offset 96 I want this dotted quad at 4 byte big-endian. So big-endian means the way it's written. So this is at 96, this is at 97, 90, 98 and 99, so I might as well just write them. B96 equals 192, B97 equals 168, B98 equals 0, and B99 equals 1. So this is somewhat primitive, and if I had more of these to write, it would be nice to find a less primitive way of doing that, but it should do the job. Let's see if I made any more mistakes. Compile exercise 4, execute exercise 4, and have a look at what came out. Exercise 4. Right, so we got a bunch of 2a, and 2a was, what was it? Had better be the 42. 42 is 2a, okay, which happens to be an asterisk, but we don't care. In fact, it prints out as asterisk. And then this asterisk here means, okay, OD is not going to bother writing out lines that are all the same. This is just the same until we get to this address, which I fear might be in octal. Anyway, if we look at the man page for OD, then this is a address output format for file offsets. Radix is one of the OXN for decimal, octal, hex, or none. So here we are talking about offsets in decimal, so we could use D, so minus capital A D. Let's see what this gives. Oh, I already put minus capital A D. So no, these were not octal, they were in decimal, and I had put it before without realizing. And what else? Oh yes, and what is the actual content is here. It is C0A80001. C0 is supposed to be 192. Well, C is 1100. So this would be 8 and 4, which makes 12 rather than 12 times 16 should be 192. Or I can look at it like that, and I say, well, if I have a C0 is this, then this is the 128, and this is 64, so 128 plus 64 is 192. Okay, so C0 is indeed 192, and A8 has got to be the other one, the 168, 0 and 1. This all looks fine. Okay, I'm not especially proud of how I generated this file, but I have generated, so let's move on. And I think after this I didn't prepare any more exercises. Okay, we've done all 4, and so let's now tackle the self-test. Okay. Write a 537 byte long binary file containing all the that is conceptually pretty similar to this one, so let's save this as self-test.c and replace this comment with self-test.text. Okay, and how do we generate that? This is going to be self-test.bin. Our buffer is now going to be 537 long, containing at byte offset blah blah, all these other things, and at the background thing which I had here for int equals blah blah, filling them all up with 42. I have to fill them all up not with a fixed number, but with I plus 100 mod 256. I plus 100 and mod 256 will basically happen by itself because it's just going into a single character, so it will be truncated. If I fear things going badly, I can just XOR it with 0xff, but that is unnecessary. Right, why don't I do something neat, which is to copy this here to say that that's the bit I'm doing now. Then I'm going to do these other things. Oops. So at byte offset 192, little-endian 64-bit representation of this horrible number. So let's say long int x64 equals this number. And then I need to copy the little-endian. It will be in little-endian in memory once I do that, because we are on haha x64. And so all I need to do is just copy the 8 bytes one by one. Now I could do this manually like this, but it's too disgusting. So what I will do is I will do a mem copy. There's a library function for that, mem copy. You will have heard of that. Memcopy function for copies n bytes from memory area source to memory area destination, just what we need. So let's and it lives in string h. So let's stick that in here. Memcopy. Copy. We need the destination first. The destination is going to be what? B192. The address of that byte. Okay. Next thing is the source, and the source is the address of x64. And how many do I stick in? Well, the size x64, which is of course 8 bytes. Right, next, at byte offset 299, null terminated ASCII string frankensteinexplains.com. So char star s equals this thing, and then I could do a memcopy of that thing as well, because it's a string and it's in C. The strings are already null terminated, not in all other languages, but here they are. So in here there will already be a null just by the action of doing this, and I can use a structCopy function which will copy everything, including the final null. Of course, nothing stops me from using memcopy again. Just for variety, I'm going to do struct copy of destination is going to be B299. Yes, what's next? The source is going to be the address of S. And or maybe just S, not too sure. Size is going to be, oh no, struct copy is, that's the advantage of using struct copy. I don't have to do the size because it will stop when it finds this null. Okay, I'm slightly unsure if this wants a constant character point, so I don't think I need to have this address in here because it's already addressed, whereas the other one needed. Right, the next thing, at every offset that's divisible by 128, big-endian 32-bit representation of this number. So at every offset divisible by 128. So first of all, I'm going to make a non-long int out of that. And then I'm gonna make myself a for loop, int I equals 0, I not exceeding 537, but going up in steps of 1 to 8. Yes, what do I stick in there? The big-endian 32-bit representation of this number. So I'm gonna get it as little-endian in here, in memory at the address ampersand x32, and I need it in big-endian, so I need to copy that in reverse. So I could do it manually like this. Again, it's a bit horrible. I want to do it slightly less horribly, so for int j to count the bytes equal 0 j less than 4. So the 4 bytes of this 32-bit word I copy into B at offset I plus j. I shift by 1 for every byte. What do I copy into it? I copy starting from the end of the thing, so x32. Now I'm going to have some kind of reference issue. So I want to get basically the base address of where x32 is indexed by j plus 4 minus j minus 1, so that's 3 minus j. So in case of j equals 0, I get it from position 3. J equals 3, I get it from position 0. So that's what I want. But now base, what's base? Base is going to be basically the address of this. So I'm going to have char star base equals address of x32. Something like that. Alright, get rid of this rubbish. And this was to write out the buffer, and that should stay the same. Okay, let's give this a go. GCC self-test.c. What's wrong here? Warning, initialization of char star from incompatible pointer type int star. So yeah, this is a pointer to int, but yeah, we're okay. Okay. We are writing in C, so we are reckless. We are doing low-level garbage anyway. So let's run this program, and the output was supposed to be self-test bin, and was supposed to be 537 bytes. Let's see. 537 bytes, that's a good start. Not that it was hard to achieve. Let's see if the content is what we expect. So self-test bin, and what we want is at byte offset 192, little-endian 64-bit representation of this, which those of you who have a bit of hacking history will have recognized a long time ago. 192 is over here. D, E, A, D, B, E, E, F. So actually the one that's easier to recognize is the big-endian one, which we find at address 128, which is here, dead beef. That's this famous hidden number was put there because it translates to dead beef. Dead beef is over here, and the reverse dead beef, and there's a straight dead beef here in 256, 128, 256. Because at every offset divisible by 128 I find this. So there's a dead beef at the beginning, there's a dead beef at 128, there's a dead beef at 256, and there's another dead beef at 384, and then another dead beef at 512, and then we run out of places to put that beef. Okay, so this is the reverse dead beef at 192 over here, dead beef that way. And then at 299, a null terminated ASCII string, frankstajano.com, we can look for it over here. So this is 5 from the end over here, and all the zeros. Was I supposed to have all these zeros? All the zeros look a bit suspicious. Ah, okay, right, because this loop didn't fill the whole array. It just stopped at 128 because it was inherited from the previous exercise. It should have said 537. Anyway, it's just a good thing that it wasn't filled up, because it makes it easy for us to see where Frank Stajano explains begins, which is here after all these zeros. And this is 288, 289, 290, 91, 92, 93, 94, 95, 96, 97, 98, and 299 is exactly where it should start. frankstajano.com, and then should end with a 0, which is indistinguishable from all the other zeros. But now that we're going to recompile this thing with the proper loop ending in here, we hope to get something better. So recompile, rerun, and let's have a look. Ah, right, now we don't have all these zeros, and instead what we have, aside from the dead beef, 68, 69, 68, blah, blah, it's all incrementing. Okay, we should start at what? It should start at 100. 0 maps to 100, and 100, we can look in here, is 64, so this should be 64, 65, 66, 67, 68, so these were the ones erased by the dead beef, 68, 69, it continues like that, all the way up to FF, where it then resets to 0, 0, and it keeps going like that. So this is all great, and FF, another round after another 256 over here. So this all looks fine, and it's interrupted by this Frank Stein explains at the place where he was last time, which was the 299. Good, so this one we checked, this one we checked, this one we checked, and this one we also just checked. And so we are happy with this result. And this is just what we were hoping to do. Now, some of this was a bit clunky actually, and maybe that's not exactly C, although it's a low-level language, it's certainly capable of doing all this stuff. Perhaps not the ideal tool for this type of job. So let's have a look at what we could do with a different tool, and let's try doing the same things using Python. So we go back to our exercise 0. No, 0, we don't care. 1. Write 1984 to binary file as the C short int, and if I load up my C exercise 1.c in here, that's how we did it in C. If we were going to do this exercise 1 in Python, then region 1984 as a C short int, then as a regular int, then as a long int. Okay. To write a binary file in Python, we write with open the file, which is going to be x1, call it x1 minus pi dot bin, so I don't override the one with the C, and I can actually compare what it was. WB is the same as the C call function as where we call it FP was what we called it in C. With this open file as FP, then from now on, what I do is FP dot write the stuff I want to write, and what I want to write is 1984 as a C short int. So 1984 2 bytes. Actually, to dereference this with the dot, I have to put brackets around it. 2 bytes, and these 2 bytes, if I look up the documentation for these 2 bytes, it's not in the man pages, I have to look it up online. Python 2 bytes, I've already looked it up another time, there we go. Built-in types, there we go. Yeah, where's 2 bytes? 2 bytes. Okay, into 2 bytes. Length, byte order, star signed equals false. So 2 bytes. The first thing is the length I want, and here I want short int, regular int, and long. Let's call it length. I could do, okay, just be simple. 2. Then the next thing is the byte order. Byte order is little-endian, and the rest is optional. I don't actually care. So this would already write 1984 as 2 bytes like this, and I could write it as a 32-bit word or a 64-bit word just by doing this. Let's see. I don't have to bother with anything else. Here I can just Python 3x1i. Syntax error, invalid syntax. What have I done? I forgot to close a bracket for a start. Okay, so this didn't complain, and what did I get for x1 pi dot bin. I got this x1 pi dot bin and x1, the one done in C, identical. So we were happy before, we are happy now. C007, C007 0 filled to 4 bytes and C007 0 filled to 8 bytes. And if I want to be more cute, I could do 4 length into 4, 8, do the length of this. Python 3 exercise 1. I expected an indented block. What I done? Ah, yes. I need to be in the form like that. Right, and now the new thing that I generated is again identical to the previous one. Great. So now exercise 2. Exercise 2.py, write this file as exercise 2, replace this with the text of exercise 2, exercise 2 the text, get this out of the way, this one, exercise 2 in C was this, right, minus 1984. Comment region here, and this is gonna write to exercise 2. For sign in -1, 1. Gonna repeat this with sign times this, except that I want them to be into complement, so signed, and actually these 2 bytes has signed false for unsigned and signed true for signed. I'm not too sure which one is the default. I should read this, but I don't care what's the default. I can just write sign equal true, because even the positive ones, they can just be represented as signed. Signed equals true, and we should be all set. So replacing all this rubbish where I have 6 times the numerical constant Python 3 exercise 2, and then what did I get as the output? I got this, which looks pretty familiar with the 2's complement version of minus 100, 1984, then this one with all the ones after it, and here, and then the positive ones. And indeed, let's check that diff x2 whatever dot bin has no difference between the 2. That's great. Excellent. So let's move on to exercise 3. I must say that I like this one somewhat better than this one, which is very very poor, and this one has some kind of flair and elegance, and it would be harder to replicate that kind of somewhat metaprogramming thing in the C part. Anyway, exercise 3 we want now. Exercise 3 is this. Looks pretty simple in the C part. Write to a binary file the numbers. Let's write this in exercise 3.py. The numbers from -10 to +10. Stick that here. Yep. First, as sign shows, and that's the one that has to be 210 bytes long. So, how long will if I be 210? Exercise 3. Here what do we write in this file? The numbers from -10 to 10 for length in sine shorts, and then sine longs is just 2 and 8. Then we write for I in range -10 to 10. No, because 10 has to be included, so we say 11. We write I, 2 bytes, length, little-endian, yes, sign true, that looks like we already done the job. And Python 3 exercise 3, and let's just go and check against the C version, and it's perfect. Great. And finally exercise 4. All right, let's copy the text of the exercise into this other file. Comment region, which I should probably make as a keyboard shortcut, which I have on another machine but not on this one, and save this as exercise 4.py, and this becomes exercise 4. Right, so I need to make myself a buffer of 128 bytes like I had here. And in Python 3, there is a thing called bytes, or byte array for the mutable version. Bytes is the immutable version, so I need a byte array because it's obviously going to be mutable if I fill it in with the background value and then I overwrite it. So byte array, and I fill it with the background of 42, and so 42 is a decimal number which I need to turn into a byte. So this could be what we've done before, which was 42 2 bytes of length 1, and big-endian or little-endian makes no difference since it's just 1 byte, like that. So that should fill up the byte array with just byte 42. And if I'm not sure about something in Python, I can always just try it in the interpreter, so I might as well just demonstrate. If I do byte array of this stuff will only do one, we'll only put one of them, but I want to have 128 of them. So how do I copy across these windows if I don't have a middle button on the mouse? This doesn't paste. Let's just maybe retyping is easy. Okay, 42.2 bytes 1 little, close this other bracket, makes a byte array of asterisk, because we saw earlier that 42 was the ASCII code for the asterisk. Okay, but what I want to do is to say I want 128 of those. Let's say I want 8, just to save 8 times this. Okay, then I get 8. If I want 128, then yep, okay, I get 128. So I do this over here, 128 of those. Is that okay? So I got my background fill of the array. Then and all I'm going to write here is write the array, write B, nothing else. And before that, I need to poke into B at offset 96 that dotted quad as 4 byte big-endian, which I've done this here in a very manual and somewhat disgusting way. See if I can. Well, I can obviously redo that here if I say B96 equals whether it's 96 is 192. 192. 2 bytes, 1 liter, all that stuff over here. Making this into a byte, and I could do that. 96, 97, 98, 99, and 192, 168, 0, and 1. Right, so that would be my job done, I think. But that's not very sexy. Bytes object cannot be interpreted as an integer. Because the sequence of bytes like this, if I take them individually, is an integer. Well, then in that case it's even easier. I just type 192, right? Like that. 192, 168. 0 and 1. And let's see if x4 has been solved. Okay, so that did the job. It's not pretty, but it did the job. If I want it to be slightly prettier, then I would, in B96, what I would do is I would put 96, I would replace 96 to 96 plus 4, that section, with bytes of 192, 168, 0, 1. I make myself a list of these 4 things, which initializes the bytes immutable as bytes, and these 4 bytes go and replace that. So that, yeah, that's more satisfactory than the other one. Okay, and now we move on to the self-test then. So self-test in C. It's too long for this screen. Okay, and now write this out as self-test in Python. Right, so we start with a 537 byte long array. Okay, 537. I make myself an expression to initialize this, which is going to be the byte I plus 100 mod 256. So I plus 100 mod 256 for I in range 537. That's going to give me all the numbers I want in a list, and then I use that to initialize my byte array, and that's going to be my background. That's very good. So that's the start of my thing. So that's this thing. Let's just do what I did last time. Stick that in here. This is this. Then at byte offset 192, little-endian 64-bit representation of that. Copy all of that. At byte offset 192, okay, so that beef, let's call it beef just so we don't get confused, is this. I meant to do this. Stick that in here. Beef is this without the semicolon, and at byte offset 192, little-endian is going to be like this. (192) to 192 plus 8. I'm going to stick beef 2 bytes, length 8, little, and the sign we don't care. Okay. Then at byte offset that S equal Frank Stajano explains .com, null terminated, which is not the default in Python, so we stick a null in here, and what we do is b 299 plus length of s equals bytes of s, like that. And at every offset divisible by 128, big-endian 32-bit representation of this thing. So for I in range 0, 537,128, so all the way up to 537, excluding in steps of 1 to 8. At every offset that is divisible by 1 to 8, which is all the i's, then I stick b of I plus 32 bits, so that's 4 words, equal beef 2 bytes, and this time it's 4, and big, and it's much cleaner than in the C version, where I had to make this double for loop, which was, was a bit disgusting. Anyway, I reckon this should do the job. Let's see whether it does. Python 3 self-test.py. String argument without an encoding. Okay, so when you encode a string, then you have to say how you do that, and let's encode it in ASCII. It's only ASCII characters, could be UTF-8. Makes no difference in this case. Right, and so if we now have a look at our self-test, shit. What did I write it to? X4 pi bin. Okay, so I overwrote the wrong file. Self-test pi bin. There we go. Rerun this thing. Python 3 self-test pi, and then, well, let's just do diff self-test the bin. They are the same, yay! Okay, so in summary, this is pretty basic stuff. We've done all these exercises in C, we've redone them in Python. It's certainly possible to do them in any programming language. I mean, it would be a pretty sad programming language if it didn't allow you to write to binary files. And so clearly you can do it any way you like. You don't have to do it in any of these things. I'm just showing you what's possible. But you have to use whatever tool you find most convenient, but learn the tool and be fluent in it, whatever your favorite tool is. It's a basic skill that you must acquire, you must have. As you have seen, Python has pretty versatile utilities for manipulating arrays of bytes, transforming integers in particular in our case, we'll be interested in transforming memory addresses into sequences of bytes, little-endian, big-endian, signed, unsigned, decimal, hex, and so on. And plus, in Python, it's not a problem to embed zeros inside strings, because Python strings can have any character, including 0. So, for example, if you wanted to send a string made of 200 capital T's to Stajano, would you be able to do that in order to, for example, to pipe it as an input to a program that you hope to overflow a buffer of? Well, in Python, as we've seen, you can just say, if you have the string T, you can say T times 200, and you get this. And if you wanted to send this to standard output, you could write a Python program, but you don't even have to, because you can just, from the command line, Python 3, minus C means now execute a command as it is. You can just say print T, see the convenience of having another flavor of quotes, and they're interchangeable, times 200, like that, and then you close the command on the shell like that, and that sends you those T's on the output without even having opened your editor to write a Python program. You can just do it on the command line. You can pipe that to some other program that accepts it as its input, like that. If you wanted, for example, you can do rather more elaborate things than that, still in a one-liner. If you wanted to write, for example, the numbers from 1 to 100, yeah, no problem. You would print I for I in range 100, like that, and there you go. Well, that's not exactly what I said. If I wanted to print on standard output the numbers from 1 to 100, first of all, this is from 0 to 99. Then it's got the brackets of a list. If I just say I just want those numbers, then I would say print rep of I, so it's a string, for I in range of I plus 1, so that I don't get it off by 1. So this is a list of strings that contain numbers, and I can join them with just with a space. Like that. And there we go. And if I wanted to put commas in between all of them, but a period at the end of the last one, I could do that as well. I could just join them with a comma here, and then over here I would say plus this. Right? Isn't that a beauty? So all this stuff you can just do as a one-liner without even writing a program that you then have to save and keep track of, and so on and so on. So Python is a versatile tool for this type of little hacks. Anyway, it's a powerful programming language. It's versatile. It's legible, and it's kind of neat Swiss Army knife to have in your pocket, if you do security, certainly. Right, if you're new to this kind of stuff, namely writing binary files, then get some practice in now. You have the Christmas break, if you are watching that at the time that I publish it, and do that well ahead of the actual security course, which will come in a few months. It's easy stuff, these things, and it's fun to do. It will pay lots of dividends. I'm gonna have a few more introductory tutorials like this for other things that I expect you to be able to do by the time we begin the security course. If you are new to this kind of stuff, then get some practice in now, well ahead of the actual security course I'll be teaching in a few months. It's easy, it's fun, and it will pay lots of dividends. Don't forget to like, subscribe, and share this video on your social media profiles, and I'll see you in the next one. Once again, Merry Christmas.